So moving on to the third talk in the signal processing track, we have Dr. Praful Pai with us. The title of his talk is Of Transforms and Models, Deep Learning for Signal Processing Applications. Praful is associated with the education team at MathWorks India, where he primarily works with academia in India towards making STEM education engaging and accelerating research using Matlab and Simulink. He completed his undergraduate studies in biomedical engineering from Manipal Institute of Technology and his MS and PhD from the Department of Electronics and Electrical Communication Engineering at Indian Institute of Technology, Kharagpur, where he focused on non-invasive blood glucose monitoring using photoacoustics. Prior to joining MathWorks, he was a R&D engineer and later a research scientist at National Brain Research Centre Gurgaon, where he worked on developing an MRI brain template for the Indian population. He is passionate about learning, teaching, and research in multidisciplinary domains involving instrumentation, signal processing, statistics, and machine learning. Welcome, Dr. Praful Pai, and I'll hand it over to you now.
Uh, yeah, thanks, Swati, for that kind introduction. So, yeah, let me just begin by sharing my screen. Uh, so, I apologize for keeping my camera off. I think there's like constant internet issues at times. So. Mm, yeah. I hope this is visible. Uh,
Yes, it's visible.
all right. All right. Great. Thanks for confirming. Um, yeah. So, should we begin right away? Should we wait till 11, or is that fine?
No, I think you can begin now.
All right. All right. Great. Uh, So good morning, everyone. Thanks for joining in for this talk in the Shannon State Talk series. And thanks for inviting us to present. So my name is Praful. As I work in the education team at MathWorks, where my focus is on working with researchers, faculty, and students on Matlab and Simulink use across different domains. So joining me today is also my colleague Amit, who works with the education team, where his work primarily focuses on application of machine learning or deep learning and related techniques across different domains. He has kindly agreed to help support this interaction. So as the title says, like we'll be focusing on deep learning for signal processing applications. And since we are from the MathWorks, we will look at how deep learning for signals work in Matlab and Simulink at a very high level. So I just maybe I thought of like putting in this this comic here for good measure, seeing that it's for Shannon's Day. So those were our introductions. Maybe we can begin by spending a little more time to know each other better. So can you please use the chat to answer the following? I am not sure how many people have joined in, but if you are joining in on YouTube or on the Meet link, uh, if you could answer these, that would be really helpful. Also, while this is more of a talk, we just have an hour. Please not wait till the end to ask any questions that pop up during the presentation. Put them in the chat box right away, and we'll try to answer them. Right. So I'll just wait for a brief moment here to kind of uh, look at any questions which have come up. All right. I don't see any at the moment. We'll just begin and hopefully please put those in whenever they come up. All right then. Okay, so I can see a couple from I can see Amit on there as well as okay John. He's from a electronics background. He started using Matlab recently and he's just doing a course here. There are others who are working on signal processing, wireless communication since 2001. That's really great to know. I think you have seen Matlab in maybe almost all its modern revisions. Uh, and there were others who are using it since 2019. All right, uh, that's, uh, that's really good to know. And in terms of like projects, I think people have worked on communications. There, Vishnu, he says he hasn't worked on deep learning projects yet, but he is doing a course in neural networks. All right. Thanks for all the answers. I think it's really kind of good to have some sort of background on the audience, uh, and we'll try to kind of cover this. Yeah. So, as I said, please don't wait till the end to kind of put in any questions, and we can go ahead. So the objective of the talk today is just to highlight applications for deep learning, primarily in signal processing, because speech, audio, and acoustic applications are amongst the largest and fastest growing application areas for deep learning after computer vision. Also, deep learning can be fairly hard, not only to understand, but also to put into practice and to put into practice well. So it's especially so for signal processing experts who haven't had specific uh, training in machine learning. Right? So, and finally, speech, audio, or acoustic applications, which we'll primarily look at in this interaction, tend to require more domain-specific knowledge or domain, which beyond which is normally required uh, uh, or beyond what is normally included under the umbrella of deep learning. So to get started and to be productive, you may need a little bit more than a generic deep learning introduction. So keeping these 3 points in mind, this is our high-level agenda for the next 45 minutes or so. We'll try to cover some Q&A towards the very end. So we'll start with a few basic ideas on what deep learning really means, where can it be relevant to audio signals, and what to expect as a final user. These concepts transition pretty well to other types of signals as well, but we'll see there are some very specific audio-related things there. Then we'll move on to looking at how we can design, train, and a fairly simple deep learning model for speech command recognition. We may just have a quick overview of how we can uh, take this trained model and also uh, have it run on a particular hardware platform. Finally, we'll try to go a little bit in depth and on a handful of selected topics, primarily to understand help you understand where to go next. Right? So let's get started with some definitions and a few things. So, what is deep learning? Uh, so deep learning is a type of machine learning algorithm in which models learn to perform highly complex tasks from image, time series, or text data. So deep learning is usually implemented using neural networks. And we're talking about learning because it's all about training these neural networks. So you can think of these as a bunch of nodes, and at each node, you're doing some linear algebra. So we can uh, train the neural network and make it learn things by optimizing parameters which are there in each of these nodes. We call these parameters weights, and you may have heard about the term backpropagation being used to refer to like a various family of algorithms, uh, especially used to do exactly this. So that optimization is exactly what we call learning. In terms of the deep part of deep learning, I think that's related to the number of hidden layers involved in these systems. So if you look at a basic neural network or a deep neural network, you have an input layer which takes in numeric inputs and an output layer which puts out some task related information. And then there are a bunch of hidden layers in between. So in the in deep neural networks, the number of hidden layers are quite more than what they were in regular neural networks. And these also mark the use of more recent developments which happened over neural network systems, which have been around since the late 70s. So the role of these old neural network models would typically be limited to simple tasks like maybe separating feature space. So the real intelligence in these networks would still live in the data processing used to extract features. So deep learning allowed the possibility of many different types of layers in between the data and the final consolidated part of the network. Okay. So those additional layers allow the system to create a more structured and more abstract understanding of the patterns in the data. So, uh, so you can see how layers gradually kind of try to learn different features from maybe an image which is given to the network. So some layers might look at, say, broad features like edges, then these might be combined to form shapes, which ultimately combine to form some representation of objects. And these final numeric values are given to fully connected layers, which give out some task related, which do some perform some task related operation. Right. On the flip side, though, the high number of layers and the parameters involved in each of these require require a lot of data to estimate correctly. So even with a lot of data, the complexity of the system could make the model impossible to optimize. However, the deep learning breakthroughs over the past decade primarily involved creation of new types of layers, which made these optimization problems tractable and possible to solve in practice. Correct. So the convolutional layers visible here in blue are a well-known example of this. Right? So CNNs, or in short, tend to be built as tend to be built as a repetition of specific patterns of these layers. So, and these have been proven particularly effective in a lot of these tasks. Uh, like here on the far right of the diagram, you may find that just like here on the far right of the diagram, you still find traditionally fully connected layers for the final classification task, right? So now if we'll simply simplify the network of this that is there in this diagram and simply look at the input and output, we can see that this looks like an image classifier. And classifiers are arguably the simplest type of machine learning, right? So how would this particular classifier uh, look for maybe a one-dimensional uh, data or maybe an audio clip? So in that case, this is an audio clip. So I'm yes. So in this Matlab live script, which you see playing here, so I can select out one of a collection of a short audio signal stored in an array. So on line 3 here, I am playing back audio from 5 different clips. Okay. I don't think the audio will be transmitted to you, but so right now there's a audio stream of a water stream, audio of a water stream playing, and uh, on line 4, what we are doing is we are simply passing it to a pre-trained classifier, and you can see the classifier put out some sort of uh, output. So in this case, the output is put out as maybe a dog barking or a stream or a natural sound and so on and so forth. So in this case, uh, so audio classifiers can like this can be represented very similar to like these image classifiers with a couple of obvious modifications. So what are these? So deep learning can be used in so you have your input is an audio signal, and your output here in this case is maybe a set of classes such as to which the audio signal needs to be uh, mapped to. So these can be maybe animals or natural sounds or artificial sounds created by other objects and so on. Right. So deep learning can also be used in a lot of other problems where an output is possibly inferred from an input. For example, many signal processing applications are about returning an output signal from an input signal, right? So in that case, you may call this more of a signal processing engine, or you may have application specific names like signal enhancer, right? So a few of such problems might be, say, source separation problems. So the cocktail party problem, wherein you're looking at separating uh, different audio sources from each other, is one such type where your input is an audio signal and your output is one as well, one or many as well, right? You can similarly look at uh, uh, maybe other problems such as looking at segmentation or even denoising of signals. Right? You could also have networks generate signals based on few numeric parameters. Here, you would use names such as GANs or generative adversarial networks or decoders such as those found in deep learning. Right? So in this case, using a few numeric inputs or parameters, the deep learning model generates signals. Uh, these applications might, like some examples of these applications might be in maybe in the communications domain, wherein you may want to kind of generate modulated signals uh, or these entire waveforms based on different inputs. Your inputs can be maybe uh, what type of fading the channel might introduce, or so on and so forth. Other things which other areas where such applications might occur are in, say, generation of radar waveforms for electronic warfare or such applications. Yeah. So whatever your inputs and outputs, uh, besides ensuring that the model in the middle can learn the task, what you really need is a lot of annotated data to train it. And that's the main reason why the demo that I showed a few slides ago worked so well. So that particular uh, uh, demonstration, so that running under the hood of that was uh, uh, was a Google trained was a model called YAMNet, which was developed by Google on a huge data set of annotated video, or rather annotated audio tracks from YouTube videos. So the resulting pre-trained network, YAMNet, or I'm guessing YouTube Audio Model Net, is able to classify sound types according to a fantastic hierarchical ontology of around 521 different semantic classes. Right. So if you want to kind of learn more, maybe you can just visit this link on research.google.com, and you'll get access to the data as well as related information there. So uh, this can do much more than plotting word clouds. Uh, so in this case, we use the function classify sounds, but it can do much more than just returning what is the source of the sound or so on. You can also look at uh, returning individual time intervals of these sound regions. And in fact, audio segments that were there that we selected from the drop down when in that particular clip. So these were manually extracted using these timestamps which were there in here. All right. The other thing to mention is that this comes with a function called YAMNet graph, which can help navigate the class ontology and post-process the predictions. For example, you may think of you may not care about the sound being from being a bark or a cat meowing, but you may be more interested in whether it is from an animal or whether it is from an inanimate object. All right. So uh, in this case, this graph of these models can provide useful information for you to kind of work with. All right. So classify sound is an example of a ready-to-use deep learning model uh, packaged as a single line function. All right. So there are many other such pre-trained models available, and you may discover something which you can readily use for your own application in there as well. However, you may need to also look at building your own in case you do not find one, right? And that's what we're going to talk about next. Yeah. One last thing before we move on is that this diagram of a signal classifier might be slightly misleading. So you may not just have some signal coming in and some sort of it being mapped to some sort of output. So as a vast majority of deep learning models don't really learn from or operate directly on plain time domain signals. Instead, most often, signals undergo a processing step. So this can either involve maybe time frequency transformations or some sort of feature extraction. Right? So the few cases where networks do operate on raw data directly are often referred to as end-to-end learning. However, that's only a very small subset of deep learning. Uh, so, for example, when we use that YAMNet model from Google to classify sounds, so it automatically took in the audio clip, but also internally it computed these transformations and time frequency transformations and features, and provided it in the right format for YAMNet to consume. We'll talk a little bit more about this towards the end of the talk. So in summary, uh, when developing your own deep learning model, the three most basic things that you need are a network that can learn the task by optimizing parameters, enough data to learn it from, uh, and uh, and also the right signal processing algorithms to prepare your data. So we'll look at a practical example to see how to do all this, and it will be a real-time speech command recognition algorithm. Okay. So let me begin by initially showing what the end result will look like, and then we can go into some of the details and have a high level overview of how you can go about doing similar such applications. Right? So again, there might be some audio playing which isn't transmitting here. So essentially, there is a person saying something. Uh, so just like Yamnet, the network used here was a CNN, uh, although somewhat smaller in nature. So what was happening was there was this. This is a recording of the audio signal. Uh, which was being recorded, like which was being acquired, and you could see the network or the deep neural network understanding commands from this live audio, which as it came in, right? So this network was trained on another smaller data set released by Google called the speech command data set, and we'll say more about that shortly. But what happens is this uh, audio is transformed into a specific time frequency representation called the Bach spectrogram, which is here. Uh, and then this is presented to the network. And this entire uh, thing, that is the signal processing as well as the deep neural network, is running on a Raspberry Pi. So what happened in Matlab was it just acquired the audio, plotted it on the time scope here, and sent the audio clip to the Raspberry Pi via UDP. And the spectrogram and the predictions were computed on board, and it sent back both the prediction and the spectrogram back to the computer via UDP. Right? You can also maybe acquire audio directly from the Raspberry Pi as well, and that also is possible. Okay. So you can review all the code for this example at your own pace simply by searching speech command recognition using deep learning. Right? Yeah. So this example is available online. I've put a link to this, but it should be fairly easy to kind of to do that. Uh, so Amit, if you want to kind of maybe paste this in, please feel free. There's also a companion example, which is the speech command recognition using Raspberry Pi. Yeah. So that concludes our introduction and our overview of just using a pre-developed deep learning tool for audio and speech signals. Now let's dive into some more specifics from the first example and look at how we can build such a model in practice. So we'll start from the data set, and I'll walk us through the main steps down to running the trained model in real time. Right. Uh, so while reviewing the example offline, so you can get code from the Matlab documentation. So here, you simply have to navigate to open script button at the top right of the page. So we've captured all of these code views here, and to more easily point things out. And we'll just use these rather than jumping into Matlab just because there is lack of time. We just have an hour. Um, but you'll just have to maybe take my word for it that this runs. So the part about developing the model is starts around, yeah. So we'll just, yeah. So it starts at around this in this region. So you're loading speech commands. So it essentially downloads this data set from a particular URL. So right now this is a URL on the this data set is hosted on the Mathworks website, but you can use similar functions to kind of download data directly in Matlab. rather than kind of you managing this separately. Uh, uh, so as I already mentioned, it uses the speech command dataset released by Google in 2017. Um, so the data here was collected, labeled, and packaged to allow development of a system that recognizes these 10 vocal commands which are listed here, right? And it tells them apart from other random words, maybe a name or something or the other. Okay, so it was released along with a blog post as well as a research paper, and in addition, Google threw in a sample mobile app for good measure. So once you download it, you have thousands of 1 second recordings uh, in a simple folder hierarchy. Okay, with each bottom level folder you can see on here named after the word spoken in the recordings within. All right. So uh, again, all the recordings last for nearly 1 second, with around 3,500 files uh, each, uh, for about 30 individual words, including words that are not actually commands. Right. So when you have such a large amount of data and high number of files, it is important to step out of the file handling details, as you don't want to be writing all the file handling code yourself. So if you worked with maybe say data that you yourself have acquired, maybe from an oscilloscope or some sort of data logger, right? You know what I'm talking about. So you may have like loads and loads of files, and essentially the file management itself takes so much time that you have lesser and lesser time to work on the actual algorithm. Right? So so here, if you see on line 199, uh, we only pass the root folder of the dataset, and we pass this to what we call an audio data store object. Uh, so this takes care of quite a few things itself. Uh, to start with, you can also maybe look at some of the other options, right? So you look at other options which are given to this function, such as including subfolders, as well as filtering by particular file extensions, and if you look at this last one, label source as folder names, right? So what does this audio data store object give us? So it gives us all the audio files that it found. So this is around more than 51,000 files. It and each of these files is also associated with its label, right? If you see here, uh, so this label is essentially the name of the folder that it was found in. So from this label source, this was automatically taken in and associated. All right. Uh, so it also ensures that these labels and file names are linked, and I can operate on these files simply through their labels. So think of these data stores as pointers to various to this particular data set. Okay. Now, what we need to do is we need to take all of these recordings over here and organize them in a way that our deep learning model can learn from. All right. So here's how we do it. Uh, First, we determine which subset of words we call commands. So as I mentioned, so there were 10 words which were seen as commands, and the others are words which are non-commands, right? So these 10 words are yes, no, up, down, left, right, on, off, stop, or go. Right? So we took uh, these particular words and we call them commands. Um, and whatever is not uh, like all other words, we mark them as unknown. All right. Yeah. Then we pick a a random 20% of the remaining words, okay, and relabel all of these as unknown. Uh, so, uh, so we have taken the remaining unknown words, okay, and we've labeled 20% of them as unknown, but the rest have their own sort of labels. Right? So these will be used to train the model. These 20% uh, of the words which are labeled as unknown will be used to train the model and tell apart essentially the random words from the actual commands. All right. Now, based on these definitions, we can build a new subset of the original data store that only includes what we need. Okay. So we essentially create a new subset which have uh, like only data that we require, and we essentially count each label. All right. So notice that we did most, like all of these things simply by using some sort of logical operations around the labels. So we didn't write low-level commands to maybe say browse through the folder hierarchy, list its contents, go through specific file names, file types, and so on and so forth. So this is what I was talking about when when I was mentioning like when you handle a large amount of files and do low-level code to kind of do these things. Right? So now we are only left with maybe 11 sets of labeled recordings. So 10 of the commands and one unknown. Okay? So with each of these, if you see the count, each of these has around 1800 files roughly. Uh, However, the unknown one has three times as many, around 6,500 or so, right? So now, once these data and annotations are ready to go, uh, like remember what we said about the need to transform the signals into a format that the network can consume. So here, uh, uh, I'll, so we turn the raw recordings to uh, a time frequency representation, right? So you can call these time frequency representations as spectrograms, and then there are many types of these. Okay, so don't worry about how we computed these and what are the functions involved. That's not the objective of the talk. The objective is just to inform that you will need to transform this, and you may transform it into through one of many such transformations. Okay. We'll talk a little bit later on how you can go through each of these transformations as well. All right. So in this case, we are showing the use of bark spectrograms. All right, and we do it through this particular object called the audio feature extractor. We'll talk about this a little bit more, as I said. So uh, you can see that there are a bunch of these parameters to choose from. Typically, like these are related to how you buffer these signals. So essentially, how you take windows of of these signals, and essentially how detailed do you want the frequency analysis to be. So it's something like frame duration and your hop duration. Yep. So you can also go with default values, and these primarily will affect your time and frequency resolution. And uh, depending upon the type of signals that you're working with, you'll find that many of those, many similar types, uh, uh, like many signals might have preset or predetermined values of what might be good choices for these parameters. For example, if you're working with, say, speech signals, you may see signal buffers in the region of 20 to 30 milliseconds. Right? So these parameters affect the size of the time frequency arrays which are produced by the transformations. So, for example, in this case, when you transform the first time domain when you transform, say, 1 second of the time domain signal, what you get is essentially 98 time slices and 50-point frequency spectra. Okay, so this bit of code is just an example based on a random file from a data set. Uh, what happens when we are looking to apply this to like the 51,000 odd files that we have, right? So in that case, you may also want to think a little bit about efficiency and how you can go about doing this uh, as fast as possible, right? So uh, this particular section of code shows how you can distribute this feature extraction task across CPU cores available on your machine, or even using GPUs. Okay, so this particular section uses par_for, or uh, par_for stands for parallel for loops. So it it will actually execute in parallel, uh, like independent loops which work on each of these uh, files. All right. So note that the data store here itself makes this like particularly easy to code. Yeah. So you can also, as I said, accelerate this further using GPUs, but we'll not cover that right here in much more detail. Right. So um, in this example, we show you we're looking at how we can extract all features at once, and that's the easiest and definitely the recommended way of doing things if your entire transformed data set fits in memory, or you could go ahead and store it again on disk as well. Okay. In other situations, you may need to do this feature extraction on the fly. Okay. Uh, you may need to do this as the network trains, and you kind of get the next audio sample in, or so on. Okay. So audio data store does make that possible, but we will not look at that example right now. Okay. So uh, it takes some time to kind of uh, complete the entire data set, and then you can go ahead and look at maybe 3 random samples from the source data. All right. Uh, so we'll just look at what the data files themselves look like, and what does the transform data look like. All right. So these are these plots here. Okay. So at the top, you notice that there are 16,000 samples. Of on the audio signal. So this is like 1 second of the audio clip, which is sampled at 16 kilohertz. And if you see below, there are only 98 points in time, 98 points on the x-axis on the transformed data. Also, each vertical slice of the spectrogram comes from a time buffer, partially overlapping with the previous one. So, this is based on like parameters which you set when you used audio feature extractor, right? So there are roughly there are 50 points over here in the frequency, and this 98 cross 50 is a particularly low number for ordinary spectrograms. But for the Bach spectrogram or other types of auditory spectrograms, which distribute frequencies more efficiently to a near logarithmic scale, this is enough. All right. We'll talk a little bit more on whether this low number of points will be able to kind of do the task. We'll look at that towards in a little bit more time. Right. So on one hand, this allows to have like a frequency scale that better reflects how we hear signals, and likely the density of information in speech signals. And also, uh, it also helps limit the complexity of the network and its training process. All right. So think of giving this entire 16,000 samples to the network to train, and that many computations, doing that many computations. And in comparison, you're giving, say, a 2D representation of this, which is quite smaller in the number of samples which are there, right? So this is also more computationally efficient. So once the data transformation is complete, this is maybe you can just maybe see how many files we processed and so on. So you can look at the training distribution on the top, and you can see, like, maybe something like 2,000 files for training and maybe 7,000 unknown data set. And below you have a smaller validation data set, right? So while training data is the data that the network uses for optimizing its weights, the validation data is a different data set which the network hasn't seen during training. All right. So essentially, we measure performance on the validation data, and it that gives us a good indication of how the network can generalize and how much it has actually learned the task that we are trying to get it to learn. Right? So, so you can see, like, the fraction of data required is, almost 1/10. So now that the data is ready, let's look at how we can use it, and specifically how we can define network architecture. Uh, So generally speaking, you may like define the network architecture based on a research paper. So the one that I have here, for example, explicitly references the application that we are trying to build. Okay, so when looking at papers like this, you can look at maybe this section, like sections which mention the type, things like the type of layers used and specific parameters in each of these layers. All right. So if you know how to read that information, you can express in Matlab these layers as a vector. Okay. So you can see here how these you've simply used the concatenation, the square brackets for this concatenation operator in Matlab to combine a bunch of these layers, such as image input, convolutional, ReLUs, and pooling layers, and so on. Okay. Yeah. So also, however, you may also find it difficult to match the description in the paper with exact programming syntax. So at least for the first time, you may want to kind of do this using an interactive app. And this is somewhere, this is where an app called Deep Network Designer comes into play. So if you go to the apps tab, it should be present there. Uh, and yeah, so as you can see, to start with, there are a bunch of these layers which are available on the left-hand side. You can see things like convolutional layers, LSTM layers, nonlinear activation, pooling, a bunch of such layers, and also a bunch of properties on the right. So you can change these layers if change these properties if you want anything from the different values, from the default values. You can compose your networks by simply dragging and dropping these in, and you can stack them in a typical CNN pattern made of convolutional, batch, ReLUs, and pooling layers. So you may also end up creating a few of these stacks, repeating a few of these stacks. So you can do that easily by simply dragging and dropping, as was seen. Okay. So in our case, the network was already built programmatically. So you can also use Deep Network Designer to view these networks. So you can see how these networks look like. So you have beyond the input layer, there are several convolutional layers and a fully connected and softmax layer at the very end. Okay. So in this case, yeah. So in the last column here, you can see like how many number of parameters this network needs to learn and where they belong and so on. So yeah, so you can see when analyzing the network, you can look at how many number of parameters this network needs to learn, as well as where are these parameters located. And as expected, they are primarily in the convolutional and the fully connected layers. Okay. So now that you have the network, we can simply proceed by training it. So in principle, it's essentially a optimization problem, and it is you can call it back propagation. And to run it in Matlab, what you need to do is simply define some training options, such as, say, the optimizer, learning rates, the number of epochs and batch sizes, and so on, and call a function called train network. Right. So you can go ahead with default values and then adjust them as you go ahead, and then you can see how this works. So you can experiment with these to kind of look at what these parameters mean, how do they influence the learning, and so on. Okay. So simply executing this kicks off the training process, and and I'll just show a clip of this executing on a network machine equipped with a GPU. Okay, so if this particular section is run, yeah, it's common to follow the progress through a graphical monitoring tool. So we've accelerated this. So the top plot shows the accuracy improving in percentage units, and the blue is for training data, and the black dots here are the validation data sets. So they update less frequently. And in this case, we've reached about 94% of validation accuracy in somewhere like 4.5 minutes on a GPU. Okay, so uh, so we didn't really have to set anything else. If you have a GPU on board, using it will identify this automatically and work with that. All right. Uh, Now, along with this quantitative evaluation, you may also need to kind of look at how your model performs in the real world, right? So, how will it perform when used with a speaker? So, so in this case, you can simply kind of write an like read an audio buffer. Take inputs from a sound card and continuously on a while loop, and give it to the network and see what it puts out. Okay, so so you can simply read an audio buffer and extract audio features and put it to give it to the classifier terrain and simply plot this. Okay, we can see this in action in a little bit. Yeah, I'll not go into much detail. Just because we have little time remaining, so we'll just go over some of this code and yeah. So in addition to this example, you can go over this example, which is like essentially how you can embed this on a Raspberry Pi board and work with that. So we'll get a new live script. I'll not go over specific parts here, but you can essentially optimize it for the ARM architecture, which is present on the Raspberry Pi, and also profile it to see if it executes in real time. How much time does each of the steps take in execution? All right. So yeah, so you can deploy your deep learning models to CPUs. You can generate C++ code for working on Raspberry Pis, or if you're working on GPUs, you can generate CUDA code, or even if you're working with FPGAs, whether from Xilinx or Intel or Microsemi, you can generate FPGA code or HDL code for your FPGAs or SoC systems. All right. So, uh, so this concludes like most of the example. So we looked at what it was to use deep learning before, and prepared like how we can use it to classify sounds. And we looked at how we can use large data sets as well as how we can prepare this data quickly. Okay. We'll just do a quick dive on some key topics, or we can also look at maybe questions which are there at this point in time. So let me just check to see if there are any questions here. Uh, yeah, I think Amit's answered most of them. Uh, yeah, yeah. So we'll just maybe continue and then again pause for questions in a little bit. So um, so we with the speech command recognition, we saw how we can create networks from scratch in MATLAB, either programmatically or using Deep Network Designer. And in many cases, these networks might already be put out by other research groups, such as from other universities, right? And they might be in different deep learning frameworks. So you can work with all of these models by importing them into MATLAB. So there is a Keras and Cafe importer which works directly, and in our 2021 we also introduced a TensorFlow importer. And MathWorks is part of the Onyx consortium, which helps like you can exchange frame models built in other frameworks into MATLAB, and you can also export MATLAB models to all of these frameworks. All right. So a lot of these deep learning models might already be available in Deep Network Designer or you can view these in the documentation as well. All right. So if you look at this section on the documentation, you can see there is there is an object on pre-trained networks for audio. All right. So YAMNet is what you can find here amongst other networks. All right. So yeah, we'll just go over this. Next, let's talk a little bit about audio data and annotations. So a data set like what we used will most probably not be available when you tackle your own research problems. So an important takeaway here is like in industry, a lot of industry use devotes time towards data engineering than to network engineering. Uh, mm, and these specific charts on the right hand side come from a talk given by Andrea Karpathy, who's the head of AI at Tesla. So his point is that the emphasis and interest towards network engineering, which is found very often in academic research, is it has nothing to do with what happens in industry, where creating the right data really is the key concern. All right. And this sentiment is also echoed by others like Francois Chollet, who's the creator of Keras, or Andrew Ning, whom you may have heard of in the deep learning context. So my second takeaway is that training deep neural networks often requires these huge data sets, but validation data sets do not really need to be as big. And so strategies for building these data sets might be radically different. So very often when building your validation data sets, those need to be really accurate, and which you can create using, say, programmatic apps such as the audio labeler or signal labeler, which is present in MATLAB. All right. So validation data sets need to be really, really accurate. Training data sets a little less so. Yeah. So you can also create and repurpose large annotated signal sets programmatically. So uh, you can do automated labeling on using highly capable pre-trained networks, or you can repurpose a lot of existing annotated data that you have. Okay. So some capabilities here, I've just put them summarize them in this slide. So note, for example, the speech to text, which you can use to wrap around cloud-based speech APIs from external providers such as from Google and so on, and the classify sound function, which we've seen earlier. All right. So you can use these to kind of create and repurpose large data sets that you have. Also, you may also look at data synthesis or augmentation for larger and better data sets. So you can create totally new artificial data with such a level of fidelity that it will allow the model to learn about patterns existing in real data. So in here, the text to speech function, which wraps around cloud speech APIs from Google or IBM or Microsoft Azure, is something that you can look at. All right. So uh, also another example here might be the audio data augmenter object, which configures and randomizes uh, like different sort of audio artifacts. So it can maybe take in the original audio signal, change its pitch, stretch it, add different sort of noises or reverb signals there, and help you augment your entire data set. Yeah. So finally, I'll just take maybe a minute more here. So finally, when computing spectrograms or many other audio features, it's very common to divide signal into buffers, as I said, and these buffers could be mutually overlapping for better time resolution, or these might be based on like most simply an FFT or a similar operation. Uh, or these time frequency transforms are used very often with network types which were like originally designed to work with images. So these time frequency transformations, the 2D representations of the signal which it generates, you can essentially give them to your convolutional neural networks and have them perform the classification task. So when working with speech or other audible signals, you often tend to kind of also look at more advanced type of spectrograms with frequency scales which have been adapted to different models of human perception. Uh, so, uh, so these spectrograms might be more compact and in comparison to a normal FFT or a regular time frequency spectrogram, and these might still retain a good level of perceptual detail, right? So, so in this case, like say something like the Bach filter bank, which we used, so essentially has a bunch of these filters, which you can see increase in width and decrease in amplitude as frequency increases. And this is essentially to model human perception, which is more selective at lower frequencies and is not as sensitive at higher frequencies. All right. So we can reorganize information by projecting raw FFT points onto this and uh, have them create like a smaller Bach spectrogram, which is if you see here has lesser time points and also might be more like grainier in comparison to this. Right? If you see this picture versus this picture, you can see like how much reduction in the amount of information might have occurred here. All right. So yeah. So you may require like all of these different sort of techniques, such as Mel, Bach, or other spectrograms or other spectral descriptors, such as cepstral coefficients and so on. Or you can also use deep learning for extracting a bunch of different signal features. Right. We'll not look at this. I think we've already gone over time. So I'll just maybe look at quickly summarizing this. So if you look at deep learning for signals, essentially you have these four operations broadly. So you may have event detection, signal segmentation itself, signal classification, what we looked at, or signal denoising or signal processing applications. All right. So talking about a summary of how deep learning in MATLAB has evolved. So while MATLAB has had the ability to train neural networks in the mid 90s with the initial release of the neural network toolbox, so we officially started supporting deep learning in 2016 and continue to update and add major functionality with each release. Uh, so I think it's one of the fastest and the uh, largest updates in every release. And some of these focus on apps, some on productivity, and some on deployment workflows. And one thing that I would really want to point at is it has now over 200 examples across multiple domains, right from audio signals to communications to so on and so forth. And these slides themselves are a bit dated. So there's the 2021 release is already out, and it's another big one, which adds a lot more functionality there. All right. So moving on from training artificial neural networks to the natural ones in our brains, here are a number of resources which you can use to learn further. So there are free 2-hour tutorials which you can use to get started. These are the signal processing on-ramp or deep learning on-ramp. There's also a longer course on deep learning with Matlab, which should be available on Matlab Academy. And we can maybe get together further to kind of have like a sort of hands-on sort of interaction later in time. There's also deep learning training which is there, but it's fully online, and in case you're teaching deep learning, do not hesitate to contact us. We'll be happy to kind of assist with uh, with supporting that course. So finally, I think I also wanted to highlight this particular student competition, which is currently on. So this is the Audio Engineering Society student competition, which is co-organized by MathWorks, and its submission deadline is close by, but you can explore this in case you're interested. So MathWorks also supports, since this is an IEEE event. So MathWorks is a sponsor for the IEEE Signal Processing Society Signal Processing Cup. However, the competition has just closed, I think, on April 26th. And it's primarily an undergraduate competition, but the research problems there are pretty useful to kind of look at. So you can also look at that in case you're interested. So apologies for going over time by 8 minutes. We could maybe do a quick Q&A, or if not, I think Amit's answered most of the queries as I can see. So yeah, thanks everyone for listening in. I think I do not see any particular questions here, but
Thank you, Dr. Praful, for such a wonderful talk on using deep learning for audio signals in MATLAB. Dr. Praful, could you please turn on your video for a moment so that we can take a picture if that's possible?
sure. Let me do that. So I actually put on, I'm not sure if you can see this, but maybe a IEEE t-shirt which I got when I was volunteering with the student branch at IIT Kharagpur. But yeah,
Yeah, it's visible. Okay,
sure.
thank you.
Thanks.
So, on behalf of IEEE-IISc Communications Society, we would like to present you this plaque as a token of our appreciation. Thank you. It was a wonderful talk.
Thanks. It was a pleasure being here and interacting with everyone here. Yeah, thank you. Thanks a lot for the invitation.